Okay, we'll put this on record as well, right? Okay, transfer of thermal energy, that would be transfer, heat transfer, just the heat itself. How would you define heat, right? So we define heat as the total kinetic.
Sir, temperature change from colder to hottest.
That would be heat transfer, right? So we define heat as the total kinetic energy of particles of a substance, right? That's in general, right? What is the total movement of all the particles? Definitely, we define thermal energy or associate thermal energy with the movement of particles, right? So, what we call heat, it is the total energy of the particles, right? That's the total energy. And if we, and this is measured in joules, right? So, we measure this uh, joules, okay? Now, if we define temperature, so temperature is the actual measurement that we can do because measuring thermal energy is impossible, right? So the only way to measure thermal energy is when it is exchanged, when it is moving, when there is a thermal energy transfer or heat transfer, we call it, right, from one object to another, or within that object, right, from a hotter to a colder region. That's when we say we can measure the heat energy. And how do you measure it? Using temperature. So how we define temperature? In other words, temperature should also be related to energy, right? Although it is measured in kelvins and degrees Celsius and Fahrenheit, whatever you may take it, right? So generally we say that this is the average kinetic energy, right, of particles, right, of substance. Okay, and this is measured in Kelvin, which is the SI unit, right? But we also see degree Celsius and degree Fahrenheit, which are you can say relative scales, right? And that's the absolute. Absolute means the SI unit, right? The actual one that we're supposed to be working, SI, right? Let's talk about temperature conversion, right? So, how we convert this is a little bit extra, right? I'll mark it as an extra topic here, right? This is extra topic or extra study, right? We should be able to know how to convert degree Fahrenheit, degrees Celsius, and Kelvin. I practically actually consider this as a joke, right? That Americans they couldn't find anything to differentiate themselves from rest of the world, so they invented a new word called Fahrenheit, right? And that's they created, and then they said that it's equal to a certain value, right? For no reason, just because they wanted to differentiate themselves from the world. Has no technical understanding whatsoever, right? They just had to create a new scale for it. So initially the world was working with degrees Celsius. So if we convert temperature in degree Fahrenheit, right, that would be equal to temperature in degrees Celsius, right, plus 9 divided by 5, right, into this. Sorry, right. Let me just do this again. Right, it is 9 by 5, right, into temperature degrees Celsius plus 32. Like out of nowhere, 32. Why? I mean, there's no explanation to this. Why there's 32, right? So Americans had to create a entirely random scale we call Fahrenheit, right? So I mean, you'll find the internet. I mean, if you go to uh, on internet, you'll find so many people, so many scientists making jokes of this, right? I don't know whether you guys enjoy scientific jokes or not. Like I enjoy those a lot, right? Being a scientist and being an engineer. So this is the biggest laughing stock that the Americans have on them, right? The world laughs at them for creating this scale. Why there is a 9 divided by 5 and why there's a 32? No explanation, right? And you ask them what are the spellings of Fahrenheit, they themselves cannot spell it. So
यार
as I said,
ये
it's
यूज
a
होता है
laughing
पर
stock. Sorry?
ये यूज होता है कहीं?
And beta, I mean, this is used in the medical sciences, right? And that's the only application we found, right? For Americans only. The rest of the world uses degree Celsius. Keep in mind, they still use degree Celsius, right? It's just a little bit more. It has a better resolution, so to say, right? Technically speaking, that's the
Sir,
only advantage you can get. Yes, Rumesa?
sir, ये important है?
Degree Fahrenheit or this formula?
Yes, yes,
Beta,
sir.
you see this scale every day in your house. That's why I'm discussing this, right? It's related to temperature. The actual scale is basically Kelvin scale, right? And that's the absolute. And that's a historical idea that we used to think that 0 degrees Celsius was the lowest temperature possible on Earth, right? Initially. But when scientists went deeper into the, condensation and all these processes, they came to know that there are temperatures which are below zero, right? And Serbia, I mean, minus 57, we call it now, right? So why the minus? Because can I measure your height in minus length? I mean, is it possible? Can I say you're
No,
minus
No.
50 kilograms, right?
no,
No.
no,
Mm.
sir.
So if you remember, we talked about base quantities, right? All the base quantities that exist, they are absolute in nature. They cannot have a negative value. You cannot have negative value for light. You can have you can't have negative value for mass or time. Time doesn't go the backwards, right? So all these quantities, base quantities, there's 7 of them we studied, right? None of them can have a negative quantity, right? And that's the problem, that why temperature is having a negative quantity. It is a base quantity, isn't it? Right? It's the fourth base quantity that we studied: mass, time, length, temperature. Right? And then we go for current and moles and then intensity of light. 7 base quantities. How temperature is having a negative value, right? And that comes with the idea of convention, right? That old people that devised this temperature scale, they did not know that the temperatures actually in the universe go up to 0 Kelvin, or what we say minus 273 degrees Celsius, right? That's the lowest technically possible temperature, right? Possible, but we actually can say that as an impossible temperature, right? In practical ways, why we cannot achieve this? Not even in the universe can we achieve, because that's too low of temperature for the particles to uh, exist inherently, right? They'll start collapsing. The electrons would not have enough energy, or you can say all matter at this point will stop moving. We do know that what is the movement of particles in solids? Yes, anyone could tell me?
They are tightly packed together.
They're tightly packed together in fixed
They're
positions.
vibrating.
Vibratory motion, right? So vibratory motion, so they're vibrating. So if we cool them down, their vibration is becoming slower and slower and slower. Up to a point, they should stop moving, right? But that point is very dangerous point, right? Because at that point, the forces of attraction will dominate, right? The things that are keeping the particles away from one another are gone, right? The repulsors are gone, because that was causing the vibration. Now, since the vibration is gone, all the particles will now solidify, including all air, everything will turn into a solid, right? Every gas in the universe will be turned into a solid, right?
सर तो कौन सा माइनस टेम्परेचर है जो कि थोड़ा है कि दैट पार्टिकल्स और मैटर भी एग्जिस्ट कर सकें?
No, we have achieved it, right? We have achieved it, by the way, right? We have achieved up to minus 271 degrees Celsius. That is just 2 degrees away from absolute collapse, right? Absolute collapse. That's just my 2 degrees, and we say that practically it can be achieved for an atom or two, but that's a test or quantum level discussion, right? Very advanced experimentation, we call it, right? Quantum experimentation, where we achieve 0 Kelvin. Other than that, in practical ways, we cannot go lower than minus 271, because energy will flow in from somewhere, right? Your sensor will is also generating heat, right? Your electronics is generating heat. So machinery that you're using to generate that temperature, the chamber in which you're trying to achieve bulk temperature, it will lose energy. You cannot have absolute pure insulator, right? Some particles will still be conducting energy, right? So that's the problem. So let's talk about the Kelvin scale, right? The absolute scale. So these are relative scales. Relative means they can have a negative values, right? So these are both relative scales, degree Fahrenheit and degrees Celsius, right, are relative scales. And relative scales mean they can have negative values. Oh, just give me a second, right? Okay. Now, when we talk about negative values, we have to find a scale that is not negative, and that is what we call as the absolute scale of temperature, which is Kelvin, right? And if you remember, the tiny little print that I gave you in the beginning, right, to be pasted in your notebook or in your physics journal, had Kelvin scale on it rather than degrees Celsius for temperature, right? So the absolute temperature scale is basically Kelvin scale, and this is what we usually study. But degree Celsius and degree Kelvin, we use them side to side. They're relative scales of each other. It's just the Fahrenheit which is odd, right? That's the odd one out. Degree Celsius and degree Fahrenheit is very simple. So temperature in Kelvin is basically equal to temperature in degree Celsius plus 273, right? And why 273? Because we came to know that we can go up to minus 273 degrees Celsius at the point where all matter will cease to move, right? In other words, all atoms will stop. And since atoms are stopping, what we're defining temperature as average kinetic energy. Kinetic energy is moving energy of the particle when something is moving at a certain speed. Heat, what is heat? Where the kinetic energy is the total energy that is there. Now keep in mind, if we try to attain 0 Kelvin, right? 0 Kelvin, not achievable. Why we say not achievable? Because inherently some movement will still be there. One or two particle will still be colliding with the other one, so it's nearly impossible to get to 0 Kelvin, right? That's what I said, that the achievable one is minus 271 achievable, right? And that is about you can say 2 Kelvin maximum. You cannot go lower than 2 Kelvin, right? So for this, let me just show you what it means to have 0 Kelvin, right? So let's get to FET, and I'm going to show you something over there, right? Particles. Yes, gas properties, right? So gases, or we should say states of matter, right? States of matter. That would be a better one. So we're gonna have a look at temperature and how particles, right? And keep in mind, if you just play with this tool, you'll be able to express it in word, right? Whatever you see over here, you express it in words, you will get perfect score in the thermal questions, most of them regarding the particle analysis, right? So you're looking at how much temperature? 14 Kelvin, right? So if I heat it up, you see that the particles start to vibrate. Keep in mind, this is neon gas. It's a noble gas, right? Let's take a particle or oxygen gas, right, where we have molecules. So if we heat it up, it has a melting point of minus 182 degrees Celsius, right? So we can convert it into degrees Celsius, right? So it has nearly converted into gas. Particles are now getting separated. The more I heat, now the particles will separate entirely from one another, turning into pure gas, right? So this is how the particles actually behave, and we're still at minus 127 degrees Celsius. This is oxygen, right? So oxygen can be liquefied at minus 182, right? Not below, not above than that. Why? Because it's a gas, right? Gases are something else. And if you take water, right, if I cool it down, it will at 100 it boils. After 100 it will start to condense. So you see some of the particles are joining up together, they're bulking up together. This is condensation happening, right? So water is coming and building up. So in liquid, particles are close to one another, but they're still depicting random motion. These few particles which are flying around are actually vapors, right? Water vapors. We see that evaporation is happening at any point, right? So we're going to talk about evaporation today as well, right? But first we're going to have a look at the this, right? At 6 degrees Celsius, the energy is so low, the particles are less evaporating, right? And we see their movement has become less vigorous, right? They're vibrating and they're colliding less now. Now if I just go into negative, you see that they're stuck. They're vibrating, but each particle is is in its fixed position. They're not changing positions anymore, right? This is ice, right? And if I cool it even further, you see that the particle vibration has gone away, right? Now they're vibrating, but with very small amplitude, right? The amplitude has become very weak. And if I just try to bring it down to 0 Kelvin, right, that would be a little hard. You can see that the temperature scale is now stopping, right? It's nearly going very slow at minus 270, minus 271, right? Barely up to minus 272. This is again, uh, and still one or two particle is moving. Probably you can't see it, but I can see it on my screen that one and two particles still is trying to vibrate there, right? And once I'm going to go to minus 273, which it probably won't go, right? That movement should also be gone, right? So now every particle is still, no particle is moving, right?
0 केल्विन में तो चले गए -273.
We're at 0 Kelvin now, right? ये beta simulation है, right? This is a simulation. In real life, this is not possible, right? You get the idea. This is what I'm trying to explain. This is a simulation, and I'm holding the cord down. The moment I release it, one or two particles starts moving, right? It's gonna gain energy from somewhere. But still, if you look, all the particles are stuck still, and that is annihilation of matter, right? That is dangerous, right? Why dangerous? Because these forces, these vibrations keep the particles away. Now, this simulation is not designed to understand what we say quantum level forces, right? Advanced forces or advanced topics, right? This is just a basic understanding. So even tiny little heat, right? I just gave it a little bit of a whiff of energy, and you see that the particles vibrating, right? So you can say that the more you heat, the vibration increases. The more I heat it again, you can see that the vibration has become crazy. And if I heat this up, now liquid, right? And then if we just keep heating it up, you'll see all of them turning into gas. So these are state changes, and you can talk about particle changes and the energy between them, right? How the energy is varying for you. Clarified? Yes.
Yes, sir.
Yes,
So
sir.
please play with this tool. It's an amazing tool. You can also check how the pressure and this works on gases, although that's unfortunately not included in our course. So I'm not going to touch that much, right? Because you don't have gases pressure, right? So you can see
Sir, what if we put oxygen?
oxygen in there. Oh, oxygen is a gas, right? That's going to
Yes,
behave
sir.
very vigorously. You see, the particles are colliding more, so the pressure has gone
Yes,
up,
sir.
right? So pressure is basically the number of particle collisions with the wall of the container when they exert the force when they collide, right? That's particle collision, and that's what we call as pressure, right? So if I reduce the pressure or increase the volume, you see that the pressure has become less and the particles are less frequent at collisions. Clarified? Okay.
Yes.
Yes, sir.
Okay, let's get back to our board now, right? So this is why we say that the temperature scale is there. So degree Celsius scale, if I want to draw a degree Celsius scale and energy, right? Keep in mind, we can never have a temperature scale or a temperature energy scale that goes up to zero, right? That's a very fun question that I usually ask. Although it's not part of your question, right? Not asked in your paper, but Edexcel usually asks this question a lot, right? That they give you a graph and they ask you that why the temperature scale is not able to go all the way to 0 Kelvin, right? So we have the energy here of the particles, and let's say we have the temperature, which is in Kelvin, right? We always say that even at 0 Kelvin, right? This is zero. The temperature is still, the energy is still up, right? This is the temperature scale, right? I mean, versus temperature versus energy in joules, right? This is particle energy. And why is that so? Because there would be still some energy associated within the particle, and that is the movement of the electrons, right? You think that the electrons will stop moving just because you brought it down to 0 Kelvin, right? I mean, although it's very hard, but let's say you did bring it down to 0 Kelvin, there will be still particle energy left because that's the energy, the innate energy within the particle, inside the particle, the repulsion between the protons and the electrons, right? So that energy you cannot take away. If you take away that energy, all of the universe will collapse in, right? Because nothing will now stop from the electrons from collapsing into the protons. I mean, you do know that opposite poles of a magnet attract each other, right? North and south, they get attracted. So keep in mind, electron is like the south pole and proton is like the north pole. What is keeping them apart is what we call as the nuclear energy or the short range nuclear forces, right? These are strong nuclear forces within the atom that exist, right? We do not talk about that in your level, but just giving an idea, a little bit of a glimpse of the future, that or you can say detailed science if you're interested in studying this, right? Nuclear forces. By the way, it was discovered by the infamous Dr. Abdul Salam, right? The only science Nobel Prize that the Pakistan was ever able to secure, and we unfortunately do not acknowledge him much, right? He's one of the most brilliant minds that Pakistan ever had, right? He was from Mianwali, Pakistan, right? Studied in Cambridge, and he discovered this nuclear forces, right? Strong nuclear forces. He talked about it. He researched about it. All the big scientists, quantum physicists that you see around, Stephen Hawking's and whatnot, right? Einstein and all these top level scientists, they've their work collaborates with Dr. Abdul Salam's work, right? And which is this very concept, right? That there is impossible to achieve 0 Kelvin. Impossible. Why? Because if you do so, you're technically saying that you're even stopping the electrons, right? You're taking every sort of energy out of the particle. So if I try to draw this graph starting from 0 0, right? Let's say this one. What does this mean? That the total energy or energy of the particle inside the particle is zero, is gone. That means the proton and the electron, I mean, here's the proton, here's the electron, right? So the electron will technically fall in. They're opposite charges, they'll attract each other. Why the electron stays away from the neutron, or sorry, the proton or the nucleus, is because it's moving at very high speed. So it has kinetic energy, and that's the minimum energy we say it is there, right? We can never take that away. That is very hard to take away. And surprisingly, if you talk about nuclear explosions, right, that's the energy that we're trying to play with, right? That's the graph. I'm representing that energy over here in a very small fragment, but technically you interact with this short range force between the electron, proton, and the nucleus, right? The short range forces, you get yourself a nuclear fission reaction, right? Or a fusion reaction. So imagine these are the most powerful energies we're talking about, right? Just two atoms or one atom, like you break the nucleus of an atom, oh, you get an enormous amount of energy out of it, right? That's why we can never have zero, because that there's a huge amount of energy hidden inside the atom itself, right? That we're trying to harvest with the nuclear reactions, right? Other than that, when we talk about particle level or atom level or bigger level, bulk level, then we say that the energy can never reach zero, right? Hence, even with the absolute scale, the temperature reaches zero, right? Technically it can, we can say that we can have 0 Kelvin, but we can never have zero energy, right? So over here we say it is the average kinetic energy for a reason. Understood why the word average kinetic energy exists and not total kinetic energy? Clarified?
Yes.
Right? So keep in mind, that was a little bit of an extra discussion, not in your course. Unfortunately, other qualifications have this. They don't have it in you. I don't know why it was excluded. This description was excluded from your book, but it is basically the clarification of what is average kinetic energy and what is the total kinetic energy, right? Now you understand the total kinetic energy would also include the internal energies within the atom or within the particles, and temperature is going to be the average kinetic energy of the particles, right? Average, right? Not necessarily the whole energy that is hidden inside the atom, but just the average one. Hence we can go to 0 Kelvin, but still there be some energy left, because temperature is average kinetic energy. So this is total kinetic energy, right? We're trying to represent, and this is the average kinetic energy that we're trying to represent. Clarified? So that's the idea of this graph in contrast to the definitions that we have, right? And just 0 Kelvin, you're not supposed to maximum, if you want to remember, just remember this: whatever degree Celsius temperature you have, you have to add 273 into it to get to Kelvin. But when we're working with heat capacity and whatnot, we say that the delta temperature in Kelvin, sorry, not degree, we don't use the symbol of degree with it, right? Is also equal to degrees Celsius. For example, I say that the temperature was changed from 20 degrees Celsius to 80 degrees Celsius, right? So what is delta temperature C over here, right? Can you tell what is the change in temperature? Anyone? Come on, simple arithmetics.
40. No,
Huh,
60, sir.
60.
Sorry.
Yeah,
60.
60 degrees Celsius, right? Now let's convert it into Kelvin. What does this statement mean? That is why we can frankly use degrees Celsius wherever we have change in temperature. Keep in mind, if you're talking about fixed temperature, you have to use Kelvin, right? Or otherwise you have to convert degrees Celsius into Kelvins, or the other way around, whichever the question is asking, right? But in your, we always have the delta T being used, right? So when we're talking about change in temperature, we can say that the change in Kelvin temperature is equal to change in degrees Celsius. Why? It's just a 273 of addition, right? Just the 273 there. So that doesn't make much of a difference. Let's convert this, right? So degree Celsius into degree Kelvin is addition of plus 273, right? So that's gonna be 293 Kelvin, right? After conversion, right? This is temperature in Celsius, this is temperature in Kelvin, right? So if we talk about this, then 80 degrees Celsius now going to be how much? Yes,
350.
3
353.
353 Kelvin, right? And now take the difference of them. That's still gonna be 60 eventually. I mean, we just added a constant, right? We can add 100 into both of them and then subtract them. Obviously, the effect is nullified anyway, right? So that is what this statement means. Yes.
3 plus n पे
G
20.
273. Yes, we added 273 because if we go from degree Celsius into Kelvin, then we have to add 273 to it. That's a constant value that we add, right? So this is what we're adding. 20 plus 273, right? We can say 20 plus 273, and this is going to be 80 plus 273, right? So if you look at the Kelvin values, they are different from the degree Celsius, but the difference between the temperature is still going to be the same, right? Since both these values turn out to be the same, so we can say that the change in Kelvin temperature is technically change in degree Celsius. That is why in our formula, E is equal to mc delta T, where we have delta T over here, right? Change in temperature we talk about, right? We use degree Celsius, not Kelvin. Technically, we're supposed to be using Kelvin over here, right? I mean, in some of the qualifications and some scientific papers, if you're not using Kelvin there, you lose marks, right? But British papers, they use degree Celsius over there without Kelvin, right? And that's fine. And why that's fine? Because the change in Kelvin temperature and change in degree Celsius is the same, right? So the value is the same, so we don't mind. We can put delta C over there. But keep in mind, wherever you have to do work with simple T, then there's a big difference between Kelvin and temperature. We have some formulas that we work on in A levels, right? And they require you to use Kelvin, right? So over there, kids are more used to using degree Celsius, right? That Kelvin and Celsius are the same. No, they're not same. Only the change of temperature for them is the same. Their actual values are different, right? Because that's an absolute value that we are working with. So all the scientific formulas work with absolute values, right? Not the relative ones. These are relative values, okay? You can convert them back in by minus 273, right? You understand, right? It's the same. It's just a constant difference. So hence the change in temperature is the same. Clarified?
Yes, sir.
Okay.
Sir, like vice versa.
Yes, vice versa. We can go back by subtracting it. We can go forward by adding into it, right? So if this is this,
And the answer will be the same.
yeah, so that would be equal to temperature Kelvin minus 273 then, right? Backward conversion. This is from Kelvin to degree Celsius, and that one is gonna be from degree Celsius into Kelvin conversion, right? That's it. I mean, no need to memorize this. As I said, they have excluded this from your course. I mean, I'm not very happy, technically very happy with the physics course outline specifically. The chemistry one is fine, but the physics course outline is very much trimmed. So many things have been removed from your coursework that I think are essential at your level to be taught, right? I don't know why they've removed so many things, right? So heat, temperature, and now few properties that I just want to reflect on that we covered, right? Temperature properties, right? The first thing we talked about, that heat transfer, right? Heat transfer or thermal transfer. And why does it happen? It always happens from higher temperature between the object, from higher point of temperature to a lower temperature, right? So always happening from higher temperature, or particles which have higher energy, right? They move towards a zone where there is less energy, right? That's one thing, right? And the factors it depend upon, right? The rate at which this heat transfer, right? Rate of transfer. So if we talk about the rate of transfer, that depends upon number one, size of the object. Obviously, if it's bigger, let's say you have a large object, you want to transfer heat from one end to the other. Obviously, it's gonna take time, right? Size or volume of the object, the bigger it is, the more it is, right? The specific type of material that we're using. Some materials are better conductors. We talked about it, right? The wax experiment. So if you have let's say a copper pipe, a steel pipe, right? Then obviously steel is a bad conductor of heat, right? Compared to copper, which is a very good conductor of heat. Now keep in mind, bad and good are relative terms. They are still conductors. They still transfer thermal energy. They are not insulators, right? So keep in mind, weak conductor, a good conductor, bad conductor, these are relative terms. There is no absolute best conductor out there, and there is no absolute bad most conductor out there. We are trying to find more of them, right? We're trying to create alloys and whatnot. It's a very big world of materials out there, so we can always make an exceptional material by changing the properties, right? A little bit, or tweaking the properties. So that's the material type we're talking about, right? The greater the type, and number three, the difference in temperatures, right? Let's say if you're trying to cool something from 100 degrees Celsius to 20 degrees Celsius, that's going to be faster compared to 30 to 10 or 20, because there is less temperature difference. So the particle, the energy flow will be slower, right? From
The
a very
gradient isn't like this steeper.
yes, more steeper curve, right? So this is like cooling rate experiment that we're going to talk about, right? Cooling rate. This is done actually in chemistry, right? Cooling rate experiment, right? Not in physics, right? It's not done in physics. But we say that when we talk about the rate at which the temperature is falling and time, we call it the TT curve, right? In chemistry, time and temperature curve. Okay, so we have time here in seconds or minutes, and then we have temperature here, right? In degrees Celsius in chemistry. We say that this is how it works. As the time goes down, the temperature, and obviously why it does not come to zero, that is room temperature, right? This is room temperature, RTP, right? Room temperature, which is like 20 degrees Celsius, right? So obviously it's not going to go lower than 20 degrees Celsius. That it has achieved just the maximum possible lowest temperature, right? Which is the environmental temperature. So why the curve is there? Because there's large difference between the energy of the particles. So the particles dissipate that energy quicker, and as the temperature falls, the energy is moving out of the particles, or they're losing that energy. Hence the remaining energy is lowering, or you can say the liquid is becoming cooler and cooler, right? Evaporative cooling, we call it as well, right? So this is, you can say, evaporative cooling as well. So if you take a cotton swab and put it on your hand, it is more evaporative, so its cooling curve is going to be like this, right? So you can say this is going to be ethanol, right? This is the alcohol swabs that we get before injection, right? They rub our skin to clean it, and then we do it. So this is gonna be for water, let's say. And why ethanol? Because it's more evaporative in nature, right? So there are more materials which are even more evaporative than ethanol. So they're going to have a faster cooling curve because they lose temperature way more faster. They lose their energy way more faster because the particles are lighter and the particles have less attraction between them. So they just evaporate quicker, making the remaining particles have lesser and lesser energy at the back. All right. Okay, this was just a recollection. Other than that, we had done heat capacity, right? Latent heats, and a little bit of properties which were expansion. Oh, that's properties of light, right? Thermal properties, right? Expansion we talked about, right? And we talked about the rate at which expansion occurs. Obviously, solid has the least expansion because the particles are closest, and the gases expand the most because the particles are already very far away, right? So, just a little bit of recollection of what you're supposed to be doing. I had your syllabus content open here. I think I closed
Sir,
it.
will you share all these?
Sorry?
Sir, will you share all of these?
These notes, yes, I have already. I've been sharing them, right?
नहीं sir,
I'll,
Okay.
right,
वो
I'll
वो- ये
need
जो
them up. I'll need them up, beta. Just give me a little while. For example, if you look at
Okay.
the latent heat one, right? I've knitted it out a little bit, right, so that it's more readable, right? Again, I received a complaint that my notes are not much understandable. Again, keep in mind, you're not supposed to just work out my notes alone. You're supposed to look at my notes when reading the book, right? This is in conjunction with the book. This is the information that is listed in the book, but I'm just making it easier for you to understand what and how to cover that, right? So it is just a recollection of what
So, sir,
you've done.
just reading the book is enough?
No, it's fine. I mean, if you can look into the book, that should be enough, right? And if you
Okay.
don't find something understandable, then you can open up my notes and have a look at
Okay.
it. But I'm improving those notes, right? It takes me a little while
Okay.
to trim the information and match it up to the book, right? As I've done for the previous topics, right? It took me quite a while to make these, right? Obviously, it takes, a lot of raising and whatnot, and writing on the tablet is very difficult, right? So I'll
Okay.
need these out and then share you the notes as well. So no need to worry. I'll send you this thermal block just to give you a recollection that this is what you're supposed to be looking at, right? 3.4 in your syllabus document, right? That I've told you so many times to have it with you, right? We have done kinetic theory, right? Book is aside, everything aside, your paper will be asked from these points, right? Anything regarding this. So whatever they're telling you, that the kinetic energy is used to explain different states of matter, particles, solid, liquid, gas have different amounts of energy. So you should know this, right? So these things are need to be understood. We have only done energy transfers and particle motion, right? And kinetic energy, kinetic theory and the particle model, right? This is the thermal topic that we have done. In book, you have 2 chapters regarding this, right? But I don't refer to the chapter books alone because at times one chapter is separated across two of these topics, right? Two of them. So just like our forces one, right? We haven't done this waves one in between. 3.3 we haven't done this, so no need to worry about this. We'll be starting this in next, right? But energy resources, right? uh, Energy transfer, conservation of energy and forces, and center of mass, moments, lever, momentum, terminal velocity, all these topics, right? We have already covered. You can see that this was the major part, forces and their effect, which is just one chapter in your book. That is actually not just one chapter, that is like first 5 chapters that we have covered, right? So starting from force interaction, motion, resultant forces, you see the order in which they are listed is different from what the book is following, right? So it's just confusing. I've never understood. The document says a different sequence, book has a different sequence. I just follow my own sequence. You get the idea. So I make the sequence which I think that would be easiest to for the kids to understand, right? I'm talking about advanced forces, acceleration, and whatnot, and I haven't taught motion to the students. How can I explain acceleration to them without telling what speed is, right? Because acceleration is change in speed. So if you don't know speed, how can I explain acceleration to you? So makes very confusing. So even so, I just read the document and know what I want to deliver and what how I need to deliver it. After that, I plan things at my own end. Okay. So let's close it up. Inshallah, we'll get back to the topic waves in the next one after doing some worksheets. All right.
सर
Have a
वैसे
good day.
एक question है
Yes. Sorry.
सर आपके वहाँ बारिश हो रही है
Yes, it's a lot. It's heavy rain, my dear. Since last night. I mean, since 12 a.m. maybe. Yeah.
ओके
Okay. Have a good day. Bye bye. Lafez.